Did you guys have any questions that you wanted to go over? And this exciting pre-calc, right?
Not at the moment.
All right. Well, let me know if you come up with any.
Okay.
I feel like this is kind of the, I think I told you guys on Monday, this is kind of like the hard work of pre-calc. Like this is the in the details section. And then we kind of get to some other stuff later on that's new and different. Not that this isn't new or different, but this is kind of just the really detailed, like how do you find all the intercepts and the asymptotes and blah, blah, blah. Like how do you do all that stuff? And then we're going to build on that and kind of move on from that too. So on Monday, we talked about how to find the asymptotes of equations, and that was in 2.6. I'll try not to scroll too much. So I think it looked kind of intimidating, but then when everybody saw how you actually did it, it didn't seem too bad, right? The vertical asymptotes are all of where basically your denominator of your rational equation, when that equals 0, what all the zeros are of the equation, that's your vertical asymptotes. And then your horizontal asymptotes had to do with the order of your exponent, right? So if the exponent on the top was smaller than the exponent of the bottom, then the horizontal asymptote was always y equals 0. If they equaled each other, then we had a ratio. And then if the exponent on the top, the n was bigger than the exponent on the bottom, then there was no horizontal asymptote. So the reason I reviewed that is because we're going to build on that even more in 2.7. And what I would recommend for 2.7 is to keep this little chart really handy. Before I forget, we are going to chop off 43 and 45. So go ahead and cross that off. So your homework for 2.7 is 1 through 21 odd. Okay. So what this section is and why I would keep this up is that this section is basically how do we graph rational functions without a graphing calculator? And your question is, why would we do that? We have perfectly good graphing calculators that we've been using for years. And why would we do that? Well, we're going to challenge ourselves in this section, specifically in problems 9 through 21, to graph rational functions without a graphing tool. Okay. The nice thing is that we have a little checklist how to do that. And I will let you use this checklist on the test. So if I don't forget to tell you, if I forget to put it into your test, I'll let you use this little checklist. So we have a checklist how to do it. And at the end, we can always throw it into our graphing calculator and see if we did it right. So even though it sounds painful, it's not too bad. So I think the best way to go about this is to go through some examples and to kind of go through our checklist and see what it looks like if we want to graph a rational function without a graphing tool. Okay, so I want to make this like a little bigger. I want to get the top part and the bottom part, but I'm not going to get that. So I'll make it a little smaller. You guys have young eyes, right? Hello, Greta, by the way. Hello. When Greta responds in text, it comes on my phone for some reason. Well, I guess because you're on your phone, but okay. So here we go. The fun that is graphing a rational equation without a graphing tool. It's actually pretty cool that you can do it. I think it's cool that you can do it. Is it something that you're going to do every day? Not necessarily, but it's cool that you can do it. Okay, so I just totally cut that off anyway, so it doesn't really matter. So what we're going to do is number 12 first. If I can find my pen. We're going to do number 12, which is it's cut off down at the bottom, but if you have your notes, it's there. So you have P of X equals 1 minus 3x over 1 minus x. Okay, so this is my function, right? It is a rational function because it's a ratio of basically one polynomial over another polynomial. It's a ratio of two things. Okay. And so if I want to graph it, I'm going to go through these steps. So let f of x equal something in the numerator over something in the denominator. So the numerator function is n of x and the denominator function of d of x. And n of x and d of x are polynomials. So these are polynomials. They're actually linear equations, right? We have a linear equation on the top and the bottom, but it doesn't really matter. They're polynomials. We kind of get the first thing. We're in the right format. We got the right thing. All right. So the first step is that you need to simplify f if possible. Any restrictions on the domain of f not in the simplified function should be listed. So this is basically kind of what we did at the end of class Monday, where we were finding holes when we simplified, but this really can't be simplified. So step 1, done. Yay. Right? All right. Step 2, find and plot the y-intercept, if any, by evaluating f of 0. Okay, so this is like all the way old school back to algebra 1. We did it in algebra 1 and we did it in algebra 2. So we want to find the y-intercept, right? The y-intercept is basically when x equals 0, right? We figure out where our graph is intercepting y. Okay. So in order to do that, what you do for step 2 is you say, well, what happens when x equals 0? What does my f of x, f of 0 equal? In this case, it's p of 0, right? Where's my y-intercept? So if I plug in 0, I get 1 minus 3 times 0 over 1 minus 0. So basically, I get 1. So I have a y-intercept of 1, right? When x equals, basically this is telling me when x equals 0, y equals 1. I feel like I should have a separate graph for this. Give me 1 second and I have some graphing paper somewhere. Oh, let's go full page, right? We'll go full page. Okay. Oh, I don't know if it's going to let me do this. Trying to be a little bit neater here, but I don't know if it's going to let me do this. It's probably going to take up my whole page. Let's go this way a little bit. I'm just trying to make a graph so that I can have a nice, pretty graph for this class. We want a nice, pretty graph, right? Make it a little smaller. Okay. It's a little skewed, but it's going to have to work. All right. So we have a y-intercept at 0, 1, right? So if I was going to plot that, it's at 0, 1. Nope, I need a brush. 0, 1 is right here. I have 1 point on my graph. Do you remember back when you were learning how to graph linear equations and you just had to have 2 points and you were done? That was nice, right? Remember back in the day when you were doing that? All right, I will stop clicking, I promise. Okay, so there is point number 1, my y-intercept, done. Okay, so we got step 2 done. Okay, step 3, find the zeros of the numerator, if any, by setting the numerator equal to 0. Then plot the corresponding x-intercepts. Okay, so basically, step 3 is a fancy way of saying that you're going to find the x-intercepts. Okay, so the x-intercepts, remember, are down here when the graph hits x, and that's when y equals 0, right? It's when y equals 0. But what this is telling you is that there's a shortcut because we have a rational equation, right? We have something in the numerator and something in the denominator, and we want to find out when y equals 0. It should be a D, not a 0. All right, so we want to find out when y equals 0. We're finding the x-intercepts, right? We don't even have to mess with the denominator, though, because we know that the denominator can't equal 0 Because if the denominator equals 0, then we have that's when we have our asymptotes, right? So we don't even care about the denominator. In order to find the x-intercepts, all we have to do is set the numerator equal to 0. Because if the top is equal to 0, then the whole thing is equal to 0. Okay, so to find the x-intercepts, I just take the numerator, which is 1 minus 3x, and I set that equal to 0. Okay, and then I do a little math. 3x equals -1. And then that means x equals 1/3. Okay, so my x-intercept is 1/3, 0. All right, so then now I get to plot that. Oh, I made my graph way too small for that. 1/3, 0 is like somewhere right there. Right? All right, so that's on there. Not crazy helpful, but we're getting there. We have 2 points. We can't connect them yet, though, because we're graphing rational equations. They don't look anything like lines. All right, step 4. Let's get some color going here. Number 4, we have to find the zeros of the denominator, if any, by setting the denominator equal to 0. Then sketch the corresponding vertical asymptotes using dashed lines. Okay, so this is throwback to section 2.6, right? Step 4 is to find the vertical asymptotes, right? If you go back a page in your notes, the graph of f has vertical asymptotes for the zeros of d of x. So basically, when my denominator, the bottom part, equals 0, that's where my asymptotes are, right? So when x equals 1, this is my vertical asymptote. Asymptote. Okay. So then I go ahead and I draw my vertical asymptote on my graph. I should have made my graph much bigger. So, I don't know if I can do a fancy line. I'm just going to have to draw my line like this. Should be dotted because it's an asymptote, but you guys get the idea, right? So that's my vertical asymptote. Okay. What do you guess step 5 is going to be? Step 5 is going to be find and sketch any other asymptotes of the graph using dashed lines. So any other ones would be my horizontal asymptotes, right? I find my horizontal asymptotes by looking at my exponents of my equation and comparing them. So this has an exponent of 1 and this has an exponent of 1, so they equal each other, right? So therefore, my horizontal asymptote is y equals the coefficient in front of the numerator over the coefficient in front of the denominator. So this is a case where the exponents equal each other. Again, you could refer back to the page before that, right? So that means that y equals -3 over -1, or y equals 3 is going to be my horizontal asymptote. All right, so let me draw that. My young eyes can't see this. My old eyes, 1, 2, 3. Okay. I think this horizontal asymptote right there. Okay. So far, so good, right? All right, now plot at least one point between and one point between and 1 point beyond each x-intercept and vertical asymptote. So now you're kind of getting an idea of what it's going to look like, right? This curve is actually going to come in like along here, and it's going to hit right here, and then it's going to go off down here, and then the same along here. So the last step is you're going to pick a couple of points that you know are going to exist inside of here and outside of here. All right, so step 6 is basically pick a couple points. All right, so your function is p of x equals 1 minus 3x over 1 minus x. Okay, so it looks like if I would pick like when x equals -2, okay, and I'm going to plug this in mentally so you guys double check my work. When x equals -2, I don't know why my computer's doing that. X equals -2, I get 1, basically 1 plus 6 over 1 plus 2. So I get 7 over 3. So when x equals -2, p of x, or p of -2, is, what did I just say? 7 over 3. So basically when x equals -2, p of x basically equals 2.13. So like a point like up here, kind of ish, right? And then you guys can find some other points. So then the last step is to use smooth curves to complete the graph between the point and the vertical asymptotes, and excluding any points where f is not defined. So then you basically smooth it out and you make your graph. And you cheer, yay, we did it, right? You graphed a rational function without a graphing calculator. And then the first thing you do is you're like, okay, let me check in Desmos. Right? No. So Desmos, you have your function was 1 minus 3x divided by 1 minus x. Okay, so we said that we had an asymptote, well, first of all, we said that our y-intercept was at 1. So that works. And our x-intercept was at 1/3. So we got those two right. And our vertical asymptote, right? Our vertical asymptote was x equals 1. So let's see if I scroll in a little bit here. So here's x equals 1. So as it goes off, it gets closer and closer to 1, but never quite makes it to 1. Right? Here's x equals 1. And our vertical asymptote, remember, was y equals 3, which is right along here. And then we just smooth it out. So voila. Right? So you guys think you can do this?
I think I can try.
You think you can try? Probably. Doesn't it sound fun to graph without your graphing tool? It actually is pretty cool that you can graph without it. Like you can come up with these crazy graphs without a graphing tool. It's pretty awesome. All right, so I think we'll do one more, and I think we should do number 21, which is from your homework. Does that sound good? So let's see if we can graph without our graphing tool. So if you have your notes, kind of keep that checklist handy, okay? All right. Number 21 says we have, make sure I write the problem right. F of x equals 3x over x squared minus x minus 2. X squared minus x minus 2. All right, so there we go. And here's my graph off to the side. that I'll kind of work with as we go. All right, so first of all, I'm going to go through my guidelines, right? It is a rational function because the top and the bottom are both polynomials, so we're good to go. It says first step is simplify f if possible. Any restrictions on the domain not simplified should be listed. So we don't have to do anything here because we can factor the bottom, right? But that's not going to cross off with 3x, so we don't have to do anything like that. Okay. Step 2 is to find and plot the y-intercept by evaluating f of 0. Okay, so let's figure out what the y-intercept is. This is step 2. Oh, this is step 2. We're going to figure out what the y-intercept is. So f of 0 equals 3 times 0 over 0 squared minus 0 minus 2. So basically you end up with 0 divided by negative 2, which is just 0. So there is when x equals 0, y equals 0. So there's a point right there, right in the middle at the origin, right? So our y-intercept is 0. Okay. Step 3 is we're going to find the x-intercept, right? The x-intercept is nice because we just take the numerator. We don't even have to worry about the denominator. The numerator and set it equal to 0. And the x-intercept is also at 0. So 0, 0. Okay. Step 4. Step 4 basically is find the vertical asymptote, right? To find the vertical asymptote, we take the denominator and we set it equal to 0. Okay, so 1 is x squared minus x minus 2 equals 0. The easiest way to figure this out, we could figure this out using the quadratic formula, right? If we can factor this, then we can know that that's where our zeros are. And if we're really stuck, we can always use our graphing tool, right? So if we have x minus 2 and x plus 1, then I think we've actually factored it, right? So we have a 0 when x equals, or 0. We have an asymptote when x equals 2 and x equals negative 1. Okay. I need to figure out how to make my line tool draw dashes. I don't think I can make it dashed. Oh, bummer. All right, so we have an asymptote when x equals 2, which is right here. Imagine that dotted. Oh, no, at the end. Okay. I keep clicking too soon. All right. Shouldn't be that hard to draw an asymptote, especially when you're shift. There we go. And then we have one at x equals negative 1. So this is going to be interesting. We have 2 vertical asymptotes. That's not negative 1. This would be negative 1. Got 2. All right, guys. One of you guys are going to have to take over my drawing. My paint skills are not so good. Let go. There we go. All right, so I have 2 vertical asymptotes. All right, now I'm going to find my horizontal asymptotes. Okay, my horizontal asymptotes is going to be step 5 here. If I can write a line. Step 5 is my horizontal asymptotes. Horizontal, remember. Okay, so horizontal asymptotes, I'm going to compare my exponents, right? So the exponent in my denominator is bigger than the exponent in my numerator. So that means that that means it's case A, right? That the line y equals 0 is my horizontal asymptote. So basically because x squared, the squared is bigger than x, right? When I compare my exponents, then my horizontal asymptote is y equals 0. Oh, I changed that color too. I don't know, guys. So there's a horizontal asymptote here. Okay. And then, all right, so we have this information. How am I going to graph this guy? What does this look like? Well, now is when I'm going to need some points, right, that are in between my line. So, this is step 6. All right. Step 6, I'm going to need some points that go on my graph because I know where it can't be, but I'm not quite sure where it's going. All right, so if you just remember your equation is, or your function is 3x, and then it's x squared minus x minus 2. All right, let's be honest. Who's put this in their graphing calculator? Nobody yet. It's got to be a surprise, right? All right, so x equals 0 isn't going to really help me. What happens when x equals 1? What does my f of x equal? When x equals 1, I'm going to kind of do some scratch work off to the side. I get 3. That's a 3, I promise. 3 over 1 minus 1. 1 minus 1 is 0 minus 2. So negative 3 over 2. Right? X equals 1. F of x equals negative 1.5. So you got a point there. Let's do when x equals 5, right? When x equals 5, you get 15 over 25 minus 5, which is 20, minus 2, 18. 15 over 18. So a little bit less than 1, right? We can simplify that as 5/6. So when x equals 5, f of x equals 5/6. We're getting such a clear picture now, right? So I'm going to go on and on from that. I'm going to really, really cheat here, guys. And I'm going to, because you don't want to watch me calculate values, right? I am not going to show the graph. Turn off the graph. No. Let me turn off the graph so we don't get a spoiler alert here, right? Minus 2x, no, minus x minus 2. So remember the other day how we were talking about how to get a table? So if you have it in Desmos and you go here and you click convert to a table, then it'll actually give you some values. All right, so I could say, oh, well, what happens when x equals negative 6? Then y equals, my function equals negative 0.45, or what happens when it equals 10, right? So then you can get all these points to kind of get your graph points together. Or we can kind of, oops, I didn't mean to do that. Hit undo. Go back again. Or we can put our graph up and we can see, does this graph, once I get all my points together, does it match up with where I found my asymptotes to be? So I had a vertical asymptote at 2 and negative 1, horizontal asymptote at 0, right? And then what happens here at 0, 0? Is that a value that I can have? So that's actually okay there. So it kind of got canceled out with my other thing, but that one's okay. Okay. What do you guys think? Can you do it?
Probably.
You can do it. It's not too bad. And at the end, you get to check it, right? So I will make sure you keep that checklist in front of you when you're doing it. Okay. And yeah. It'll be good. Good stuff. All right. I'm actually going to go ahead and do the last section. So that means that your homework will be due not on Monday, but it'll be due on the 29th. Because this last section is so much easier if we can do it online. So, and it's one of those sections I really like. I really like this section. And your homework isn't too bad. So it's 1 through 7 odd and 11 and 16. So, and 1 through 6 are when you match the graph with the type of model. And then, so basically you have 7, 11, and 16 to do that are like this kind of heavy duty kind of problem. So what this is like one of my favorite things to do, I wish we could do it all day, is when we actually use models to model our data. Okay. And what in this section, we've only really talked about quadratic models. So basically, you're going to be looking at data and you want to say whether it can be. So just to kind of start off, if I had a science experiment, let's say, and I plotted my data, so this was like number of days and number of petals on my plant that I'm growing for my science experiment, right? And I plot it out and I get graph number 2, and you want to model this. Do you think it would be best modeled with a linear model with a line, a quadratic model, which is our parabola, or neither one? This is a trick question, right? So number 2 would clearly be a linear model, right? If you plotted this data and you want to go want to model it, you're going to do a linear model for this, right? You're going to figure out which line goes through the data. All right. Versus number 6, if you plot your data of number of days your plant is, I don't know, listening to rock music and number of leaves it has, I don't know, something like that, right? And your data looks like this. So like the number of leaves peaks and then it falls off. Then this looks like a quadratic equation, right? So we would want a quadratic model for something like this. What about number 4? Would either model really work for number 4? Number 4 is like kind of quadratic, but you kind of have this crazy one here. Oh, and this one over here. So this one is probably not going to be very modeled by either one. Okay. So in this section, we're talking about modeling, but really the only 2 types of modeling we're talking about are quadratic and linear. So you guys pretty clear on what those are? I'm going to take that as a yes. Okay. So then in exercises 7, 11, and 16, we're going to do this. So let's do number 8, which is on your homework. Okay. So you can see that the instructions are long, but it's not too difficult to do. It says, Part A, use a graphing utility to create a scatter plot of the data. B, determine whether the data could be better modeled by a linear model or a quadratic model. C, use the regression feature of a graphing utility to find a model for the data. And D, use a graphing utility to graph the model with the scatter plot. And E, create a table comparing the original data with the data given in the model. Okay, so for this, you can do all of this in your TI, right? And I can't remember. I think Mackenzie, Greta, and Connor, you guys are all using Desmos. You can also do it in Desmos. Either one works. I am more than happy to show you how to do regressions on your TI. If you have your calculator, if you're listening later, it's in your TI calculator, it's under statistics and edit. So basically, I want to make sure that if you want to know how to do it in your TI, you can. So let me know. But let's go ahead and do this in Desmos, obviously, because it's a little easier for me to put it up here and do for you guys. It'd be nice to have a virtual TI calculator too. All right, so step 1 says use a graphing utility to create a scatter plot of the data. So in Desmos, if you're going to do that, what you're going to do is you're going to go to this plus sign, and instead of adding a function, you're going to add a table. Okay, and here they give you a set of data plots. So I'm going to try to enter this pretty quickly. So you guys might need to check my work. So when x equals -2, we get 11, not with a point. -1, 10.7, 0, 10.4, 1, 10.3, 2, 10.1, 3, 9.9. And if you guys can figure out, I'm somewhat techie, but not super techie. If you guys can figure out how to screenshot this and like print it and include it in your homework, then I'm fine with, like it says, use a graphing utility to create a scatter plot of the data. So I made a scatter plot of the data. You could copy this scatter plot down onto a, you know, a graph, or if you can figure out a way to screenshot it, you're welcome to do that. However, you want to present that data is fine to me. Like I said, there's 3 problems, so kind of gives you an idea of how many you have. So I know my x's go from like, I'm going to go from like -3 to 10. Okay, and my y's, I'm definitely going to go like from 0 to, sure, 15, something like that. All right, so what I was doing there is I was just resetting my x and my y axis to make my data look a little better. All right, so here's the data. They don't tell you, they don't give you a fun explanation of what your data is, right? But here's my data. And what do you think is going to model this best? Line or quadratic? Part B, determine whether this data could be better modeled by a linear model or a quadratic model. What do we think?
Linear.
Linear, right? This is definitely a line, for sure. Okay, so part C, so that's the easy one. Use the regression feature of a graphing utility to find a model for the data. So here's my data that I put in. This is how Desmos does regressions. So you'll see here that they've named this X sub 1 and Y sub 1. So you want Desmos to pull the regression from your values of X sub 1 and Y sub 1. And what is the equation for a linear, what's the linear equation? It's always y equals mx plus b, right? So unfortunately, if you type in y equals mx plus b, Desmos doesn't know, oh, I should regress this. We have to change this a little bit. We need to tell Desmos that I want to pull my data from x sub 1, right? Because that's where my values are. Oops, hope that didn't erase that. And from y sub 1. Okay. And I want this to not be equal. I want it to approximate my data. So is that a tilde? I think tilde. So this is how you would actually tell Desmos to do a regression. Instead of the equal sign, you have to use the tilde sign. Okay. And then you need to tell it not just to pull any x's, you want the x sub 1 and y sub 1. Right. And then what it tells you is it tells you that to model this data, if I typed it in right, okay, model this data, I get a slope of -0.18449 and a y-intercept of 10.4763. Okay, this is how you model the data. All right, so that was part C, use a regression feature of a graphing utility to find the model. Part D is use a graphing utility to graph the model with the scatter plot from point A and E. So Desmos basically did that. It graphed the regression in black and the actual values in blue. So you can see how well it matches. Okay, And then the last part it wants you to do is if it wants you to create a table comparing the original data with the data given by the model. Okay, so what you can do then is you can add another column on here. Okay, and my model was, it won't let me copy it. I have a slightly different numbers written down because I use my, if you use your TI, you actually end up with a slightly different number because they must do regression differently. So it's negative 0.08x plus 10 point x. See, I need to tell it to pull from x sub 1. There we go. But I didn't get all my numbers quite right. So I need to go back down here. 10.4763. So what I'm doing right now is I'm adding a second column to my table, and that's going to let me compare what my regression is with what my actual data is. So I'm going to add a couple of 4409. There we go. Let me make this a little bigger. Here we go. Okay, so now what I have here is this is my original data, and then the green represents the linear equation that I made, right? And this tells me like when x equals -2, my actual data says it's 11, my regression would tell me it's 10.85. Okay. When x equals -1, my actual data is 10.7, my regression would give me 10.66. So pretty close, right? 0, 10.4 versus 10.47. So this is a table comparing the values, right? You can also kind of look graphically and can compare your values. Sometimes, like here and here and here and here, the regression is really good, right? These points here, you can see there's a little bit of variance on the edges. Okay. So, how do you guys feel about that? We have 5 minutes left. I don't know if you want me to dive into like number 16 at all. It's pretty okay. I think it's actually really cool. So number 16, you have it on your paper. It's actually your homework too. Is a little bit different. We'll just dive into it for like 2 minutes because I think it's so fun. So awesome. All right. The table shows in sales. Aren't you guys excited? Like my favorite thing to do. The table shows in sales S in millions of dollars for jogging and running shoes from 1998 to 2004, according to the National Sporting Goods Association. So in 1998, there were $1,469,000,000 in sales. Okay. So it says, use a graphing utility to create a scatter plot of the data. Let T represent the year with T equals 8 corresponding to 1998. So what they're saying is T represents time. And instead of putting in 1998, this was our sales, we're going to put this in as 8, 9, 10, 11, 12, 13, 14. Okay. So you would enter this data in to Desmos. All right. I'll erase this guy. So again, you go here and you add a table. So in 1998, we had 1469, 1999, 1502. One thing to do is always check your data, because if you type one number in kind of off, then, and if you are someone that likes to check your solutions, your regression might be slightly different. It just depends what tool you use. Desmos does regression slightly differently than TI has do. So, okay. So now if I go to look at my data and figure out, I plotted my data, right? If I go to look at my data and see what it looks like, I can't see it. That's because my axes are all messed up, right? So I should go from like 5 to 15 and from maybe 1300 to maybe 2000. There we go. There's my data. So what do you think this looks like? It's kind of hard to tell, but actually in part B, they say, use the regression feature of a graphing utility to find a quadratic model of this data. So what's the standard quadratic formula? So this is actually y equals ax squared plus bx plus c. That's the standard quadratic equation, right? But we don't write it like that. If we want to find regression, we got to change this to a tilde, right? But now it doesn't know which x's and y's to get from. So this needs to be x sub 1, and this needs to be x sub 1, and this needs to be y sub 1. Oh, voila. All right, so now we have a regression, and it tells you this quadratic is when A equals negative 3.07, B equals 131.9, and C equals 597.29. Right? So this would be your model of the data. Part C would be to use a graphing utility to graph the model with the scatter plot. Voila, Exhibit A. So part D is interesting. This is where I think it's interesting. It says use the model to find when sales of jogging and running shoes will exceed $2 billion. $2 billion, right? So $2 billion is $2,000 million. I mean, I just said that really weird, but it's basically when it crosses this line here, right? So if I look, it looks like around when t equals 19. So now we got to kind of reverse and figure out what that would be. So that's about 2009, if you kind of keep up their chart. Okay. Part E says, and this is kind of an opinion thing. If I zoom out on my model here, do you think that this model is a good model for predicting future sales? So do you think that this model that we just made is good for predicting sales in 2018 that we're in? So that would be in year 28, right? I don't know anything about gym shoes, but I don't think that the sales of gym shoes has dropped off, right? It's really good at modeling right in here, but our sales, I'm sure, of gym shoes have just kept going up, right? People still wear gym shoes. They wear them out. You buy new shoes, all that stuff. So I would say that in the long term, that's not a good model, but maybe in this short term, it is. All right, so that is it. I kept you guys 1 minute longer, but we did get through 2.8, right? Got through 2.8. So, yeah, thanks for sticking with me. Have fun graphing without your graphing calculator and then switching over and using your graphing calculator like crazy to do regressions, right? So thanks for coming, guys. Have a good day.
Bye. See you Monday.
Bye. See you Monday.